workshop on tree-edit distance, presented by Hector Franco. You can find me at francoph@tcd.ie. Let's start seeing the Levenshtein algorithm and the substring matching algorithm. The string distance, also known as the Levenshtein algorithm, is a precursor of the tree-edit distance, and it measured the shortest sequence of commands that transform a string S into a string T. And what it does is to count the amount of operations of swapping one character to another, deleting one character in S, or inserting one character in T. For instance, these two family names have a distance of 2 because the letter L have to be inserted on the second on T, and the letter E have to be swapped into O. So only two modifications. Computing the Levenshtein distance, it's made by calculating intermediate cost of matching substrings of the first string to the second, by that always include from the first to a certain amount of characters. So the way to do it for these two names is to create a table, fill the first row and column by ascendant numbers, and then use the Levenshtein formula to fill the rest of the table. And at the end, we will find the distance at the bottom right corner of the matrix, which means the cost of matching the whole string to the whole string of the other side. Yeah, that's the distance. Now, once we create the matrix, we can also backtrack the numbers and obtain in this way the mapping. So here we can see that n match with n without any changes. So in both cases, n is matched to 0. Here we can imagine that E and H doesn't match, so what we did is to insert the letter E. Here we have two possibilities because the C can match the first or the second letter. So we have two possible mappings for the same distance. Now I would like you to practice it on your own. Let's imagine the example between God and good. You should be already able to fill the first row and column with ascendant numbers. And probably you already have the rest of the numbers. And again, in this case, there is two possibilities because God have one O and good have 2. So you can match in any place. And the cost is 1 because in any case you have to insert an O. How about substring matching? How about having one string, in this case universe, finding a substring? Well, the algorithm will be the same, but the first row on universe will be all zeros, and that means that we can delete as many letters from the beginning of universe for free. And the answer will be not on the bottom right corner, but on the bottom. Any of the values will be good. What means that we can delete uh, characters from the back of the string for free. And we can get the alignment just in the same way. Now let's go to three-edit distance. The three-edit distance was proposed to solve what is the minimal time mapping. And Zhang and Shasha proposed an algorithm to do it. So a time mapping is a mapping in which the right to left order is preserved, so siblings cannot swap order, or the ancestry relation is preserved. So if one node is an ancestor of another, that relation should be kept after the match. And also, one node only can match another node or none, but you cannot match one node into another two nodes. Now let's pass to the basic concepts before starting explaining the algorithm. Let's start by what is a postorder, traversal postorder. The way to enumerate the nodes of a tree in traversal postorder is by first labeling the left side, then the right side, and then the node itself. Please try to practice yourself. We have to label this tree. So probably you already guessed it right. Right side, then repeat the algorithm again, and so on. And these are all the ancestors for a given node, which is very intuitive. You also need the concept of the most left descendant. So for each of these groups, the most left descendant is the one at the bottom. It doesn't have to be graphically on the left, but it means the most left means the first descendants as much as descendants you can find. Now you also need the concept of the key roots. And it's for the same groups that we made before, is the higher ancestor. So somehow for each group of most left descendants, there is only one most left descendants and one key root. And yeah, one key root could be also the most left descendant. Now let's go to maps. The concept of a mapping is very easy to understand. There are nodes that are deleted, there are nodes that are inserted, and there are nodes that are perfectly swapped without changing the content, and others are matched but swapping the content. Please note that this is not a time mapping. So it is just an illustration of a mapping and what will be the transformation. So with this definition, we have 4 sets of swaps. So the deleted, the inserted, the nodes that are swapped, that could be perfectly swapped or could be swapped with a change. A way to define mappings in a more formal way, that the mapping is, in this case, it only refers to the swaps. So S is the source, T is the target, and the map are pairs of nodes between the source and the target. Let's see the time mappings again. One-to-one, sibling order preserved, ancestor order preserved. So, let's try to practice. Let's guess if the first mapping, this one here, it's a tie mapping or not. Ready? And the answer is no. This mapping is not preserving the ancestry relation. Because, because this node here was not an ancestor of this one, but after the transformation, it became an ancestor, and this is not allowed. Can you guess for the second map? Probably you already guessed it. The answer is not again, because you cannot have multiple one node matched to multiple nodes. Can you guess the third one? Well, the third one is a possible time mapping. It might be not the less cross mapping, but indeed is a possible time mapping. And can you guess the fourth one? Again, is not a time mapping, because siblings, these two siblings, are swapping their order. So the left to right restriction is not preserved. And now let's go to the three distance algorithm. It could be multiple time mappings between two trees, but the tree distance is the distance of the less expensive possible time map. And the cost is defined as the number of insertions, deletions, or swaps. Which again, it can vary the cost from one implementation to another. Now, I want you to try to prove the triangle inequality, just as an exercise. Knowing that insertions, deletions, and swaps have the same cost. Well, I just want to mention that all possible combinations of sets lead to the same conclusion, that the triangle inequality have to be preserved. And now let's jump to the most interesting point, and probably that's why you are watching this video, the Zhang and Shasha algorithm and how to produce the alignment. Well, the first thing to know in this algorithm is that there is a tree table and there is a forest table. Sorry, a set of forest tables. So the forest distance is, well, you know, is the distance between a set of trees to another set of trees. And we are going to designate it by this lambda. So tree distance is the minimal distance between deleting the first node and swapping the forest to the second tree, inserting the first node of the second tree, and later matching, adding these cons to the tree to the forest of what we have left, or just to swap the cost of swapping both root nodes and then matching both trees, both forests. But the forest definition it's slightly different. I mean, it's exactly the same for inserting or deleting, but in order to preserve the right to the ancestry relation, then the head node is only swapped if the rest of that particular tree for which there are key roots is also preserved. So in this case, we chop off the last tree. I think I already mentioned this, that this is not allowed to check to make sure that the ancestry relation is preserved. And as you can see, this is a possible mapping. I mean, a possible mapping that is not a time mapping. And this is what could happen. And this is the pseudocode for the tree distance algorithm. So for each key root of the first tree and the second for each pair of key roots in traversal post order, well, we calculate the tree edit distance. And to calculate the tree edit distance, we create a forest table, and to know how big it should be, we create these bounds, and then we create the forest table. And again, we initialize the rows and columns with the value with an ascendant value, which in this case should be 0, 1, 2, 3 until whatever number, or whatever is the cost of deleting one element after another, which we assumed previously that is always 1. And then, when we already initialize the forest table, we go for each most left position of each node, and are equal, then, well, we calculate the minimal forest distance between the three possibilities we already inspect before. And if not, it means that we just use or the forest or the tree distance. And again, this is to calculate that if it's a tree, then well, it all in case of, sorry, let me go back. In this case, we have to calculate to get the tree distance that should be pre-calculated and another forage distance, which is this case here. Let's try to see it with a sample as more graphical as possible. In this case, let's imagine that the colors means different labels. So we have 3 different colors and we have 2 trees. The border of the nodes is different just to differentiate both trees. And now let's imagine that the most left array is something like, for the first tree is 1, then the third is itself, the fourth is itself. For the fifth node is 1 as well, and for the sixth node, the most left is 1 as well. And the key roots, will be this node is not a key root, or 1 meaning this node is a key root. So in this case, the key roots are 3, 4, and 6. Again, the most left nodes and the key roots. And now this is the table of atomic cost, which is basically checking the label, and if the labels are the same, then the cost is 0, but if the labels are different, then the cost is 1. And now let's imagine how to fill the table. So the first column is useless because we start numerating by 1. Then let's suppose that we initialize the values of the matrix with none, so not a number, just to make it easy to know which are all real values and what are not. And in this case, the matrix is 6 by 6 because that are the amount of nodes of both trees. And now we try to calculate the tree distance between the subtree 3 with the root node 3 and 4 because they are the first ones on the list. And because the trees only have one node, it seems very simple. So we can delete them or to swap. And we swap them. So we add in the tree distance table a 0 because the cost of these 2 subtrees, swapping them, is 0. Now, let's see, we repeat calculating for the subtree containing 3 and containing 4 and 3. And, well, the way was to, both are trees, so we will fill the tree table. And using our forest table, we know that swapping 3 and 3 costs 0, so why not another extra cost of 1 for inserting 4, which happened to be, well, the winner. Now we pick the roots 3 and 5 and repeat. And there are just 2 nodes, which is very easy again, and we get 1, and again we update the table. And now we pick the roots 3, the root node 3 of the first tree, and the root node 6 of the second tree, which is a lot more complex because it includes 6 nodes under itself as descendant. So we are trying to swap one tree of one node to a tree with 6 nodes. So now we try to swap 3 and 1, which is the most left node of the subtree with the root 6. And it's a tree, so we have to update the table. And the calculation is very easy again. Swapping is the best choice. And now, for the second tree, we compare to match the node 3 with the tree containing 1, 2, and 1. And again, it's very easy to operate once we know the previous result. And using our forest tree table, we got that the cost is 1 because we just insert the node 2. And in this case, it's important to know that we cannot look in diagonal because this, now what we are trying to compare, is not a tree into a tree. In that case, it has to come from the tree edit distance from the tree table. And again, in this case, seems the best option. And again, this is not a tree, but we can get the value. So we are trying to match the node 3 with a forest with 2 nodes. And here I just want to leave it and show the complete example, the alignment that would have produced. Again, these are the key roots are marked in red, and the green are the most left nodes. Now, if you imagine that God and good are trees by just creating a vertical tree, it should be easy to calculate, to use the Zhang and Shasha algorithm and get exactly the same results as with Levenstein algorithm. And in this case, we get that the forest table is exactly the same as the tree table, and the tree table is exactly the same as the Levenstein table. The interesting point is that the tree edit distance is it's very efficient in time and in space. And again, like the Levenstein, it's very easy to calculate the alignment by just backtracking where the numbers come from. if it was a swap or an alignment, or a deletion or an insertion. Thanks for your attention, and I hope this workshop was useful to understand the Zhang and Shasha algorithm on 3-edit distance.